This is my first video. I'm talking about Michael Shellenberger, the candidate for the governor of California. Basically, he's pro-nuclear and pro-nuclear power, and that's why I think you should support him. But I want to talk about nuclear power, and I have a metaphor. Okay, many people fear nuclear power because they the two things the average person fears is the waste and the possibility of a disaster like Chernobyl. I'm going to talk about not just the waste, but the nuclear fuel cycle. And most people don't understand the nature of used nuclear fuel. Let's use the term used nuclear fuel rather than spent, because there's most of the potential energy is still inside the fuel. So I'm going to talk about, give you a metaphor for how the fuel cycle goes, and I think feel free to use this at any time, anybody. If you're thinking about supporting him and you're like you think nuclear power is a little bit on the sketchy side, but okay, I'm going to use two metaphors. One metaphor is the metaphor of chopping a tree down and burning it in a furnace. The other metaphor is running a marathon. Okay, so nuclear fuel is usually, the starting point is uranium, which is a natural resource. Now, there's another element called thorium, which isn't generally used, but can be. But let's in the metaphor, let's talk about the natural resources being like trees in a forest. Okay, so the mining industry is like lumberjacks. They go out into the forest, and there are two possible original resources, which is uranium and thorium. Now think of the uranium as like trees, and the thorium is like trees. And in this forest, there's about 4 times as much thorium as there is uranium. But generally, the mining industry ignores the thorium. So the thorium is still there. Thorium is 90 on the periodic table. Uranium is 92. That means it has 90 and 92 protons respectively. Okay, so they extract the uranium. In this metaphor, it's basically chopping the tree down. Now, the uranium tree consists of the log, and then there's the branches, right? Now, the branches are easy to burn, easy to ignite, and therefore can burn. The log can't burn directly, and it's difficult to ignite. So, in this metaphor, okay, uranium is divided. There is 2 different versions of uranium usually found. One version is called uranium-238. That has 92 protons and 146 neutrons, and that's the log. That makes up 99.3% of all natural uranium. So imagine a tree with some branches, some thin branches, which you can burn as kindling. The other version of uranium is called uranium-235, and in this metaphor, that's the narrow branches which can be ignited easily into a fire, and that consists of 92 protons and 143 neutrons. So the mining industry is like the lumberjacks or the logging industry. They chop the trees down and then they take it to the sawmill. Now, they take it to the sawmill, and in this metaphor, the sawmill is the enrichment and fuel fabrication facilities. So refining, enrichment, and fuel fabrication facilities. Now, like I said, you can't just chop the kindling off, the narrow branches off, and burn it. You have to sort of cut it up in a way that the percentage gets boosted from 0.7% to higher levels. So the sawmill chops it up, and what happens is the sawmill chops up this original resource, and in the sawmill it chucks away sections of log which have less of the branch on them into a big pile. This pile is the tailings from the enrichment facility. Now, the tailings from the enrichment facility is called depleted uranium. So it's uranium with less than 0.7% of uranium-235. So the enrichment facilities, or the enrichment industry, has this big stockpile of unused logs at the back. Imagine a sawmill with logs at the back. So what they do is that they can, this particular enrichment facility, they then take it, once they fabricate the fuel, they fabricate it into fuel. It's now at high percentage of enrichment. In other words, there's a higher percentage of branch to log ratio. So it's up around, say, 3, 4, 5%, right? And they now fabricate the fuel from that. And this is what the reactors burn. Now think of the reactors in this metaphor as being furnaces. Now, there's one particular type of furnaces are optimized to burn branches. Because that's the easiest part to burn. It can ignite quickly, and so the uranium-235 in this metaphor is basically ignites easily. So what they do is they take it to the furnace, and the furnace is optimized to burn, but they're not efficient. Most of them aren't efficient enough to burn it when it's at the 0.7% ratio. There is an exception. That's called CANDU reactor, and also another exception called Magnox, which was an older British reactor. So think of these furnaces as being kindling burners, or this is where there's some of the log gets burnt. So the branches, so basically they take it to the furnace and they ignite it, and the branches burn. Right? Now, with CANDU reactors, which is a Canadian reactor, it stands for Canada Deuterium Uranium. That is more efficient, and that you can skip the enrichment process with that. You can take the original, say, cut the tree down, take it to the sawmill, and fabricate it into fuel without the boosting process of cutting up the logs. To boost the ratio of branch to log ratio. So you can skip that process, and that will get you in the game. So generally what happens is that in a nuclear reactor, the branches burn. So let's say you have the European pressurized reactor, for example. The European pressurized reactor requires 5% uranium-235 and 95% uranium-238. So, in this metaphor, the 235, the kindling, you ignite the kindling but essentially about over its 1 or 2 years that it's in operation, this furnace is going. Think of the reactors like furnaces. About 65% of that kindling gets turned to ash. So the uranium-235 gets smashed in half, and the much lighter products are messy and sticky, and they're like the ash or the soot in this equation. So, but a secondary process happened, and this secondary process is very important. And the image of a log burning, how it starts to burn, is what got me thinking about this metaphor. And as it turns out, this metaphor just happens to work pretty well. The secondary process is where the uranium-238 absorbs a neutron, becomes uranium-239, which has 147 neutrons instead of 146, and uranium-239 only has a half-life of 23.5 minutes, and it undergoes beta decay, where one of the neutrons fires off an electron and electron and an anti-neutrino. So, and it becomes a proton. So therefore, it becomes Neptunium-239, and Neptunium-239 has a half-life of 2.5 days. So, Neptunium-239 has a half-life of 2.5 days, and it does the same process and becomes Plutonium-239. Now, in this metaphor, that's the log sort of changing into charcoal. And sorry, I've got a bit of a cough here. And that's the log turning into charcoal. And the charcoal is now a consumable. It burns like charcoal, burns like kindling. It burns like the small branches, and it's very effective at burning. And now only a small part of the gets skimmed off. So let's use the European pressurized reactor as an example, which starts at about 5%. So 95% of the mass at the beginning is log, and 5% is branch. 65% of the branch immediately burns and becomes ash and soot. 2% of the total mass is the log, and this image of flames come out. When you're watching a log burn in a fire, you see the log. When you burn a log in a fire, you put kindling underneath. Hold up, I've got to stop this.